So, hi everyone, welcome to Inspiration Exchange number 48, and this is the last Inspiration Exchange of this academic year. I think we've had quite a few very interesting presentations over the year and hope you've enjoyed all of our different sessions, which you can, if you've missed out on any of them, take a look on YouTube. So today's session with ICML 2025 coming up next week is actually just about that. And I think we've got some very exciting papers and works to share with you, and hopefully that will spur a lot of discussion. So just as an overview of today's session, we'll be covering a preview of 3 papers from the lab, which will be presented at ICML 2025. The first, strategically planning a top-down approach to option generation. The second, preference learning for AI alignment, a causal perspective. And then the third, GSIM, generative simulations with large language models and gradient-free calibration. And you'll hear from all of our amazing speakers in a little bit. And please post any questions that you have for them in the Slack channel such that we can have them answered during the open discussion later. And the earlier, the better, such that you bubble up to the top. And then thereafter, we'll have a roundtable and Q&A with some very esteemed panelists, Dr. Simon Woodhead and Dr. Rafik Salama, who Tennyson will introduce once we get to the panel discussion. So I guess without further ado, let me hand over to Max.
Well, hello everyone. Thank you, Nabil, for the introduction. So I'm Max, and today with my co-author Antonin, we'll be presenting strategic planning, a top-down approach for option generation, which tackles a fundamental challenge in reinforcement learning, which is how can we make agents think and plan a little bit more like humans do, and hopefully more efficiently than current RL methods do. So problem with traditional RL has achieved very incredible things, but the problem is that it often operates bottom up. And as you can see in the top diagram here, it explores the vast space of state actions through massive trial and error. And this is okay in chess, in which you can randomly move pieces until you stumble upon a checkmate, but it is not as acceptable in other situations, such as randomly performing surgery on people until you stumble upon a successfully extracted tumor. This is inefficient, like the process that bottom-up RL follows is inefficient and unsafe, which is not acceptable for some real-world problems, as we said, in healthcare or, for instance, business strategy. In contrast, humans use a top-down strategic planning approach in which we first consider different goals and strategies that you can follow to solve this goal that we want. And then, like for instance, in this case, it would be locating cancer and then thinking about how to extracting it. And we don't consider every possible move. So our goal would be, how can we equip reinforcement learning agents with a similar kind of strategic capability? Let's make it more concrete through an example, which would be collecting meat. In this case, we'll focus on the crafter environment, which is the one that we use for most of the experiments. And the goal is collecting meat. So it's a modified version of crafter. And let's look at what a bottom-up approach would do. So here, the agent would start by learning the low-level actions, such as moving around. And by random exploration, at some point it would stumble with the fact that when you attack a cow and you find a cow and you attack it, then you can get meat. The problem is that this would work. It would take a while to get there, probably, and it's not unlikely that it would get stuck on this simple local minima that is giving this reward, and it's harder to explore to much more complex strategies. In contrast, a top-down approach would start by identifying the potential overarching strategies that we can follow. In this case, say hunting, which is the one that the bottom-up would have achieved, but also farming or trading. And for instance, if it considers farming, then it can outline the sub-goals that it needs, such as building enclosures or finding a way to breed the animals and so on. And through this strategic thinking, it would be able to discover potentially more complex and more rewarding long-term policies. So that would be the rationale. Now, the question is, what do we mean by a strategy? How can we formally define this? And in the paper, we formalize a strategy as a distribution over policies. Now, of course, there's many different distributions that we can find, and we need to put some desiderata into exactly what kind of distribution of our policies we're looking for. And these strategies should restrict the search space to a smaller, more promising subset than the original state action huge space, right? So as shown in the diagram here, we would need to balance two different things. One would be specificity, which is this concentration, the fact that we want to consider the least amount of policies that we can so that we are more efficient. And we formalize this through the entropy of this distribution of our policies that we would want to have smaller than a specific threshold. And then another property, which would be, we don't care if we have a small set of policies that we will train on, but if we don't have a good policy within this set, then we won't get any good policy out of it, right? So here in this diagram in the right, it's a little bit hard to see, but for instance, in the right, there's this purple strategy, which is this set of policies, and then there's the orange one. The purple one would correspond to a strictly more specific strategy than the orange one, and it would keep the same value because we see that the optimal policies, which are the more purple ones, are within it. Instead, on the left one, we would see the orange one, which is within the yellow one. So it's also more specific, but it would have a smaller value because it does not contain any of the more optimal strategies with policies within this subset. So the thing is, this is what leads to the strategy problem, which is given any MVP and some high-level knowledge, which is the one that will drive this generation of strategies. How can we find a distribution of our policies that will be specific and preserve most of the value that we can? So this trade-off is very intuitive, but it's also somewhat theoretically motivated. And in the paper, we provide a theorem that where we show that if we have high specificity and value, we get higher sample efficiency. The takeaway is that although we have, so here, imagine we have a normal RL method, we know that we have a complexity in the number of trajectories that we need to sample to get an epsilon optimal policy with high probability of the cardinal of the state action space. However, if we can make the specificity and value assumptions, then we know that the strategy, if the strategist provides a high specificity and high value strategy, then we can reduce this theoretically to a much a potentially much lower complexity, which would scale with the entropy of the strategy, or the inverse of specificity. So basically, it would scale with the lack of specificity. In a nutshell, this means that if we have a more focused and high quality strategy, then we can reduce the trial and error needed to find an optimal solution. Okay, so how do we achieve this in practice? So how do we put these ideas into practice? What we do is we propose the strategy agent, which is at its core, what it does, it builds a strategy trees, which breaks down this like a high level objective into sub goals. So let's go back to the meat collecting example. The root here would be the main goal, which is collecting meat, and the strategist using powered by a large language model basically would break this down into several distinct approaches, such as breeding cows, hunting with bare hands, or crafting weapon and hunting. And here it's a simple tree, but it could be deeper. In this case, we provide as an example for the crafting and then hunting. Then it could refine this further. So the deeper you are, the more specific the strategy it is. And in this case, we provide example of a different kind of more specific strategy that would be a plan node here, in which we don't necessarily go, as in the previous cases, into just more specific and narrow approach to the goal, but rather here we have a sequentiality of sub-goals that all of them need to be fulfilled in order to achieve the overall goal. The question is, like, there's a question that remains, which is, here we have a natural language strategy, but how do we translate it into something that RL can actually use, right? So the question would be, well, our answer would be, in order to keep it general and applicable to many settings, we opt for reward shaping. And in this case, what we do is we take different states, we convert them into natural language, and we use an LLM that ingests the description of the state, the strategy, and also some potential external knowledge about the system. And it uses all of this to score the specific state and score it according to how aligned it is with the strategy that we're pursuing here. And then for efficiency, but it wouldn't be theoretically necessary, we use a student network that it's trained on these samples to be able to more efficiently repeat the process of getting this kind of reward in actual training the RL model. And in practice, when we get this shaped reward, then we combine it with the true reward, as we see here below, in which we have this alpha coefficient that has this this combination. And the thing is that initially we lean more towards the shaped reward to guide more exploration towards the strategy that we are considering. And then as we get more and more trajectories, we anneal this towards zero, and then optimize more the actual reward that we care about, which is the ground truth at the end. And now I'll give the floor to Antonin to discuss the experimental setup and the experiments.
Great, thanks, Max. Just checking you can hear me okay. So I'll talk a little bit about the experimental setup we use in the paper to validate this method, and then move on to the results. So we focus on the craft environment, which Max mentioned, which is a sort of simpler version of Minecraft. You can see this is the user interface, this 2D procedurally generated world with many different types of blocks with resources you can collect, you can craft tools, you can fight mobs and collect resources you have to collect resources to stay alive, essentially. And we first start off with a sort of simpler variant of this environment, which we call the meat collection mode, which is to test the sort of this canonical example we were giving earlier of, discovering breeding instead of just going on to do hunting in order to collect meat. So in this mode, the reward gotten by the agent is purely counted as the number of meat items they collect. So you can see the cow on the top right side is the way to collect meat in the environment. And we just say that you have to collect as much meat as possible. And we also add a breeding mechanism that is not in the original environment, where you can give a sapling to a cow and it will essentially duplicate the cow. And so there's, with this modified environment, there's this very clear option that appears in order to collect meat. You could either go on to just hunt cows directly and collect the meat immediately, or take a little bit more time, do these extra steps of collecting saplings and then giving them to cows to breed them and be able to collect meat more effectively eventually. And then after that, we also run our method on the original environment, where originally the reward is counted as the number of achievements unlocked in a single trajectory. And these achievements cover a wide range of different things you can do in this world. So it ranges from collecting specific resources, fighting and killing zombies or skeletons, the sort of enemies, or crafting specific tools. And so we'll see after how this gives rise to a more complex range of strategies and how methods performs in this more complex setting. So on the next slide, we first see on the meat collection mode This is comparing, so here we use, obviously the underlying oral agent that we use is a free choice, as we'll see later. So in this one, we start with a simple PPO algorithm and compare our strategy driven agent to the vanilla PPO agent. And you can see on the right side, so the strategies proposed are the ones presented by Max. So mostly we focus on the breeding and hunting strategy. And on the plot on the right side, you see that the PPO line in red painstakingly, gradually learns to collect meat over these 2 million iterations. And meanwhile, the strategies, the strategy-based agents, such as the blue line for breed and the green line for hunting, learn much more quickly to collect meat. And you can see that the green line, the hunting strategy, very quickly gets the hang of collecting meat by killing cows, but then it plateaus because there's only so much you can get from this strategy without breeding cows, because at some point you start not having any cows around. So like this example gifs of the trajectory of the two agents on the bottom left, you see that the hunting strategy is done killing all the cows it could find, and now it's kind of thinking about what it's done. It can't do much more. Whereas the breeding strategy keeps spawning more cows thanks to the breeding mechanism. And you can see that in the bottom line, the bottom subplot on the right side, that this shows sapling to cow, essentially how many times the agent has given saplings to breed cow, essentially. And you see that only the blue line, the breeding-based strategies, is unlocking this mechanism pretty early on. And thanks to that, it's reaching a much better, much higher reward than the other two. So this kind of illustrates the power of this top-down approach, where just knowing the right strategy in the first place is a very powerful prior to steer the behavior of the agents for more rewarding strategies. Now, in the next slide, we also show how. So in the first one, we're using a simple PPO agent, but of course, the strategist agent is sort of orthogonal to the choice of oral agent that is used and actually trained on the environment. The only thing that the strategist is doing at the end of the day is providing this sort of shaped rewards that is trying to steer the agent towards a particular strategy. But then the actual agent that is being trained on this shape reward can be arbitrarily chosen. And so here we show that you can take a more complex agent. This is EEDI from Jiang, and which is essentially under the hood, it's basically quantile regression, deep learning, with some extra bits and bobs for increased exploration. It's one of the top performing methods on the crafter environment. And you can see this is the same environment as before, and now the vanilla performance is much higher because the base agent is more powerful. It's more efficient at exploring the environment and coming up with strong behavior on its own. And yet it still benefits from the strategy guided steering. So you can see that similarly to the previous results, the breeding strategy eventually is the one that outperforms the other thanks to the breeding mechanism. And what's interesting here is you can see the vanilla method in the middle graph is essentially learning to extend the length of the episode, so surviving longer, and that's the main way with which it's performing better and better over time. But it doesn't learn to breed, as shown by the bottom quadrant. So you can see how in practice, in effect, this is sort of another implicit strategy being done by the vanilla IDE, but it's not the most valuable one because it's the breeding strategy that eventually takes more reward. So yeah, we can move on to the next slide. Finally, a third result is now we turn to the original crafter environment, where it's not about collecting meat anymore. It's about just performing as many different achievements as possible within one trajectory. And as I said, there's about 20 or 22 single achievements in crafter that are very different from each other. And so running the strategy, building a strategy tree on this gives rise to more complex, more diverse approaches. So we show here the four main approaches, the four main strategies found for crafting, fighting, collecting resources, and watching over survival needs. And in the top right graph, show that essentially each of these agents trained on these individual strategies behave in a way that is very qualitatively aligned with the intended strategy. So you see that the crafting strategy achieves the craft-related achievements much more efficiently than the baseline, the vanilla agent, and same for the fight and the resources. The strategy needs is sort of on par with the vanilla agent, and that's because actually fulfilling these achievements are pretty basic. They're among the achievements that are first discovered with the vanilla method. So the strategy is not as important for these, but we can see that for this more complex behavior, like collecting more advanced materials and crafting more advanced tools, the strategy makes a big difference. And in the bottom, the GIFs show you sort of this qualitative change in behavior. You can see that the fighting one is interacting more with the mobs here at the bottom, which is a zombie or a skeleton. And the craft and resources are putting more effort into exploring, gathering resources and crafting tools. Yeah, I think we can conclude here. So in the next slide, just a couple of takeaways. So we propose this top-down strategic problem as a way to bridge the gap between how traditional RL algorithms currently learn in this bottom-up fashion, and in contrast how humans typically approach decision making problems. We leverage the general knowledge and reasoning capabilities of LLMs to generate and evaluate strategies, and then propose this reward shaping approach to translate them into and to help guide RL agents' behavior through reward steering. And we show that we validate leads to faster learning, higher performance, and more complex behavior. Future direction include closing the loop. So at the moment, we're generating the strategy tree, training RL agents on it, but then what would be very interesting is provide feedback to the strategist agent as to how each of the strategies performed and how qualitatively they behave, so that the strategist can refine its understanding of the problem, which strategies would be most promising. And then another interesting direction would be allowing the agent to switch between strategies mid-task, as we know that sometimes the optimal behavior is a mixture of different strategies depending on what the current trajectory entails. So yeah, thanks a lot for your attention. Let us know if you have any question in the Slack, and I'll give the floor back to Max and Sam for the next paper.
Thanks. So now that we know that the top-down approach is powerful, but it still relies on having an environment to learn in, and in many domains, we don't have this luxury. So in this second paper, we will discuss some work that we did jointly with Samuel Holt and Anton Mihaela, which is GSIM, generative simulations with LLMs and gradient-free calibration. So the question that we ask here is, what if we need to build the simulator itself? So why would we want this? First, simulations are essential because they allow us to ask what if questions, and this can look differently in different situations. But for instance, we might want to test a policy that we might want to implement in a hospital without necessarily risking the test itself in practice. We also might want to stress test systems before necessarily encountering this situation. So for instance, what would happen to a supply chain if there's a sudden disruption? Or we might also want to empirically or use this the simulation to optimize resource allocation, such as, for instance, what would be the best policy that we can use to allocate beds in a given a specific pandemic with specific characteristics. So what is the problem, though? That building by hand these simulators is very slow, it's very expensive, and requires a lot of domain expertise. But this, at its turn, also constitutes an opportunity for us to try to automate this process through the large, vast knowledge of large language models, and also the increasing amount of some kind of data availability, even if it might be limited and potentially scattered. Okay, so in order to design a good simulator builder, we would need to understand what are the desiderata for for a simulator, a good simulator. So what constitutes a good simulator? First, it's crucial that it allows for plausible generalization. This is the core property that would allow us to ask what-if questions where in situations that we have not seen. So basically, we want it to be reliable outside of distribution. And this is something that we could expect from simulators that have been coded by LLMs, which is the left column, the LLM-driven column, but not from purely data-driven methods, which probably lack inductive bias to generalize out of distribution. And even the LLM-coded simulations have a problem here, which relates very much with the second desiderata, which is the empirical alignment. So, of course, given the data that we have, we want our simulator to match the observations and the behavior that we observe in practice. And this also helps in part for generalization, of course. And the problem for most LLM-coded simulations is that this is not usually necessarily the case. But on the other hand, we have this from purely data-driven simulators. Additionally, we also want to ensure that the data, like the type of data that we generate, is consistent with reality. So, for instance, we wouldn't want a simulator that gives us fractional people or things like that, because in some situations you might want to be faithful to the distribution and the data type. We have interrogants here because you could achieve it with these methods, but it's not always the case that you always have these data form consistency. And finally, we also want to ask the actual question, right? What if? And what if shouldn't be necessarily what if we change a specific input, but it could be potentially what if we change a component of the system or things that do not constitute inherently inputs. So can we intervene on the components? This is something that is very hard for purely data-driven systems because they are very little intervenable. And it's possible to do with LLM-coded simulations as long as they are reasonably interpretable. Okay, so how can we get the best of both worlds? So we go into a hybrid framework, which is GSIM, that has three main steps. The first would be the LLM structural design, which is basically having an LLM guided by domain knowledge proposing the simulator structure, which should contain the causal links in the form of code. And this somewhat causality aware design is what should allow for plausible generalization and also potentially empirical alignment. Now, on the second step, we need to calibrate against the data. So we use the available data and the current structural design, and then we have a set of parameters which the LLM has left as potentially undefined or with a prior. And then we can use different techniques such as evolutionary strategies or simulation-based inference to tune these numerical parameters to match the observational data that we have. And then once we have this, we can iterate. And we can iterate by using an LLM that, well, together the LLM and the numerical results from the empirical grounding or the calibration, we can see how this current structure optimized the data and how much it fitted and in what ways it failed. And we can convert this into natural language feedback that can be used again by the LLM to propose a new structural design and feed again and so on and so forth. So this cycle ensures that at the end of the cycle, ideally, the simulator should be both causally plausible, thanks to the LLM prior knowledge, and empirically grounded, as guaranteed in principle by the empirical grounding and the refinement. And now I'll pass the floor to Sam to discuss the method and the results.
Great. Yeah, thank you so much, Max. That's really, really exciting. So I'll go through now the method and exactly how it works. So as Max was saying, a user will actually come along with a data set, as we see here, and then most importantly, actually some sort of textual description, which will really describe what we want to model here. And it's completely autonomous end to end. So after this step, then it would actually initially generate quite a verbose, detailed user, essentially environment code. And then what we do then is we actually have two approaches to actually fit or calibrate this initial simulation to the observation data set that we have. So we have, as Max mentioned, simulation-based inference and also evolutionary strategies. And actually, we support both of these. So just to give you a quick teaser on how simulation-based inference works. So initially, we start with a prior, and then we can actually simulate from this prior different parameters, and then we can actually use our model, existing model, and actually simulate an entire data set. And then we can actually train a surrogate model, at which point they actually kind of the reverse mapping, such we can actually condition on our observed data set to then recover an actual distribution over all the possible parameters. And this is really powerful, and this is one of the first works to actually marry LLM or environment generation or model generation with simulation-based inference. So check out the code for more details there. We also have another approach actually, which is very robust and actually may actually be the most optimal for what you want to do, and that's evolutionary strategies. So in this case, we can actually start with a population of candidates or parameters in the model, and then construct a fitness loss function, which essentially is mean squared error for how well we actually fit to the observed data set. And then we can iterate this through genetic programming approaches such as crossover or mutation, and then actually update the initial distribution and then resample new distributions from this in this evolutionary strategy approach. And this overall gives us a very good estimate of one single kind of delta, if you will, of parameters. So it depends whether we want some sort of approximation or prior of the parameters. But overall, actually, what that leads us to then is a very accurate fitting simulation calibrated to the real data that we have. And that's really powerful. But then actually to go beyond and actually iterate the model, what we can do is we can actually subsequently iterate the model in subsequent steps through, in this case, giving kind of in-context learning example pairs of what the previous environment models were, reflecting verbally and using this technique of LLM reflection for LLM agents to actually improve the model and actually give verbal kind of descriptions of maybe where the environment model is incorrect and can actually be fixed. At such point, we then regenerate the code model, and then we can actually refit the simulator code, and then hopefully we actually get a lower validation loss. And actually, this is kind of we keep a buffer of the top kind of K models that we generate through the process, so we're always keeping the most accurate model, if you will. And we repeat this for a number of iterations, normally about configurable by the user by about 20 or 16, at which point we then end up with the very final, in this case, environment model, which is hopefully quite accurate and actually fitting the observed data that we have. So where can we use this? So particularly we added three kind of use cases within the paper, which we evaluated. So one was actually looking at COVID-19 modeling, so SAR models and discrete feature and stochastic environments there. But one of the most important things we were very excited about is actually modeling supply chains. So modeling famous economic supply chains like the beer game, for instance, as we presented in the paper, where you actually partially observe states and then actually demand fluctuation and you get stochastic different transitions within in the environment, and then you get different kind of components at different steps from maybe the factory or a multi-step supply chain, which is quite nice. And then another more complex environment, if you will, is in this case, we tried to create an initial version of a hospital bed scheduling approach for different diseases within some sort of hospital and fitted to some sort of simulated amount of data. And this is kind of quite interesting because if we can kind of model more complex environments, then this is actually is hopefully quite a useful tool for others to use. And here we actually have different stochastic arrival rates for different diseases, lengths of stays, and also mortality for different patient kind of classes, if you will. So when we look at actually the related work methods, so how does our method compare? So there's been some excellent related work by many others in the field, such as WorldCoder or data-driven world models. And what we do is obviously we do use a large language model to come up with the code. So we do actually benefit from these structural priors. And we can also have quite a lot of flexibility on the actual data that we support. And then we can do empirical calibration. And also because obviously we have some sort of initial model that we've iterated on, we can also hopefully actually accurately, well, as well as we can, model out of distribution data that we haven't seen before. That's always an art, but hopefully actually having a more constrained model, smaller kind of spacer model, and then fitting that to the observed data, hopefully will actually allow us to kind of model out of distribution events. So when we actually look at the overall results, as we see here, what we see is some of the kind of larger transformer models, if you will, deep neural network models, and or kind of scientific discovery methods as well. Also comparable with two ablations that we ran with the method. And then also, which is really nice, is we natively support out of the box optimizing with evolutionary strategies or optimizing with simulation-based inference. And actually, simulation-based inference, as you can see here, actually, it seems to maybe potentially be one of the most promising ways to optimize environments like this. Also, what's quite interesting, so this is the COVID-19 environment models that we could kind of get out of the model. And what's really nice is about having some sort of model with parameters fit, we can also kind of test different counterfactual scenarios or test different scenarios in this case. So this COVID model 19, we can actually model the different kind of transmissibility parameter within the model and then forward simulate. And actually the full lines are the actual ground truth values and the dotted lines are the predicted values. So we can actually model all sorts of different, in this case, lockdown intervention policies and different kind of, in this case, strengths of maybe COVID to really model different possible scenarios, which is quite nice. And another approach as well is actually, if we have a really good model, then as Max alluded to in the beginning, we can actually use this for policy optimization, which I think is actually some great future work that others can build on top of our environment generation approach to really optimize really good policies. And there's all sorts of work so you can do that. But one of the things we did was just initially actually model essentially the true policy and then model what policy could be optimized using our environments. And what we can see is we can actually kind of recover the optimal policy by actually optimizing with a simulated environment. On the top here. And also we did the same for a kind of a heat map for the supply chain or beer game problem on the bottom right as well. And essentially the take-home message is this is actually possible to use for policy optimization as well. And just to conclude in next steps, so really significant step is actually toward automated simulator construction. And this really provides plausible generalization, empirical alignment, and data form consistency, and actually allows system-wide experimentation. And really gradient-free optimization or simulation-based inference makes it really flexible to a wide range of real-world systems. Although we do have limitations, of course, so scalability, so it could be computationally intensive, particularly for high-dimensional systems to fit this or iterate over this, or even just use very expensive LLMs, depending on the use. And also it can actually depend on the LLM availability to propose reasonable structures. Of course, more accurate LLMs would always give you better responses, and we saw this within the results. I think we have some appendix results which prove that. And SBI can also be quantify parameter uncertainty, which we think is really exciting future work, and actually can be used by others as well. And actually some future work as well is people can use adversarial environment design as well, as we're seeing with new works as well. So thank you for your time.
My name is Kasia, and today I'm going to present my ICML paper titled Preference Learning for AI Alignment, a Causal Perspective. So in this project, we consider the problem of LLM alignment, which is the part of the LLM training process, which ensures that the model's outputs are generally safe, reliable, and aligned with human values. The most common approach for aligning LLMs is the so-called RLHF, that is reinforcement learning from human feedback. And RLHF consists of two steps. There is the reward modeling step and the subsequent LLM policy optimization. These reward models are trained on data sets of human preferences. Such preference data sets are often collected in the following way. A user submits a prompt to the language model, and the language model generates two candidate responses. The user then decides which of the two responses is better according to their own judgment. Such collected preference data sets can be just generally represented in the following way. And we have tuples of prompts, responses, and binary choices indicating which response was preferred by the user for the given prompt. And then the reward models are trained commonly based on the Bradley-Terry-Luce model, which essentially says that one response is preferred over the other based on based on which reward for which response is higher. So here the sigma represents the sigmoid function. And so alignment and safety of LLMs is largely reliant on the robustness of these reward models. And in this paper, we ask whether the current practices in preference learning suffice for robust reward modeling. In order to examine this problem, we apply a causal framework to reward learning from observational preference data. In this paper, we decided to adopt the convention of the potential outcomes framework. And specifically, we let the tuple X, Y, and Y prime, which is the prompt response and the second response, correspond to the treatment received by an individual. We also introduced the notion of potential rewards, that is, hypothetical rewards an individual would assign to a given treatment if it was received. And in this case, the treatment is this combination of prompt and the two responses. And analogously, we can also define potential outcomes as the potential preference choice made under the assigned treatment. If we use the BDL model to describe the relationship between the rewards and the observed labels, then the expected potential outcome is directly determined by the difference in the potential rewards of the two candidate responses. And in this causal framing, a key question is whether the expected potential outcomes are identifiable. In our paper, we adopt the standard causal assumptions to the preference learning setup. Namely, we introduce the following three assumptions. Consistency, which says that if we observe X, Y, and Y prime, then the observed outcome is equal to the potential outcome under the given treatment. Then there is the unconfoundedness, which states that the potential outcomes are independent of the assigned treatment. And thirdly, there is unconditional positivity, which guarantees that the assignment of prompts and responses is non-deterministic. And together, these preconditions are sufficient to guarantee that the expected potential outcome is identifiable and can be estimated in a non-parametric way. However, these assumptions are not sufficient to estimate potential outcomes for previously unobserved treatments, so for previously unobserved prompts and responses, which is what we ultimately care about. And to enable generalization, we introduce a model of latent treatments. In this model, we assume that the content of prompts and responses can be effectively summarized into a set of latent factors, and such latent factors can carry meaning, for instance, the style of the response or its conciseness or correctness. With the latent treatment model, it requires weaker assumptions than the previous one to guarantee identifiability. So we introduce the assumption of latent sufficiency, which essentially states that the rewards are a function of the latent factors. That is, rewards are conditionally independent of the original raw text given the latent factors. And secondly, there is the assumption of latent positivity instead of positivity now, which requires that all combinations of latent factors have a non-zero probability of being assigned. And they're also non-deterministic. So now we can just swap assumption 3 for assumptions 4 and 5 to be able to guarantee identifiability and non-parametric estimability of our expected potential outcome. Great, but what does it all mean for practitioners? The key takeaways from our paper are the following. Latent factors cannot be perfectly correlated, as otherwise the assumption of latent positivity would fail. For instance, suppose that we consider just two factors, completeness and conciseness. Complete responses often require elaboration, making succinct yet complete responses possibly very rarely observable. And that is a problem, because then we cannot disentangle the two effects of completeness and conciseness from each other. And then secondly, there cannot be any unobserved confounders, which can become an issue if user-specific variables influence the internal utility of users. For instance, the unobservable expertise level of a user may influence both the type of prompts that a user writes and also their subsequent preference choices. And in this paper, we focus a lot of attention on the problem of confounding. In particular, we stress that unconfoundedness can be easily violated. This can be the case if the prompts X are not randomly assigned but written by the individuals who then score the generated responses. As a result, users scoring the LLM's responses of one kind may differ systematically in certain way from users scoring responses of another kind. And so we can formalize this by introducing a user-specific contextual variable, which is represented on these graphs with a C letter. And that variable influences, in the case of self-written prompts, the variable influences both the prompts and the rewards assigned to the given treatment, which introduces the confounding effect, as presented here on the graph on the right-hand side. To empirically investigate the impact of confounding in the observable data on the robustness of the trained reward models, we perform an experiment based on the popular HH-RLHF dataset. In this dataset, prompts are written by two groups of laborers. There is one group identified by C equals 0, who focus on assessing the harmlessness of the responses. And there is the second group, labeled by C equal to 1, who focus on assessing the helpfulness of the responses. But both of these groups have different objectives. So because of the different objectives, they tend to write the prompts in a slightly different way. And then also their rewards assigned to the individual prompts and responses, they also will be different because the objective C is sometimes conflicting for the objective of helpfulness versus the objective of harmlessness. So a given response can be helpful, but at the same time it can be harmful, in which case there is a conflict between the two objectives. So we generate semi-synthetic data based on the original data set to control the degree of confounding in our data set. And we also know that in the original data set, it demonstrates a perfect confounding effect because the objective directly determines the kind of prompt that the user writes. So if this confounding is really a problem, then it's quite interesting that the original data set has this almost perfect confounding effect there. And our goal is to train a conditional reward model. So that is a reward model that can be conditioned on the user-specific objective. Here, it's helpfulness or harmlessness. So we want the reward model to behave differently depending on the setting of C equal to 0 or C equal to 1. And we introduce 3 models. There is the base model, which first takes a given pair of prompt and the response, and it embeds it with an LLM to a one vector of like an embedding vector, and that embedding vector is concatenated with the objective, which then is passed through an NLP to obtain the final reward. The second model that we consider is a multi-head model, which instead of concatenating the objective at the MLP, it introduces 2 predictive heads, one for the objective C equal to 0, and the other one for C equal to 1. And this architecture mimics the structure of the causal graph, wherein the latent factors are independent of the objective given the prompt and the response. Finally, inspired by prior works on causality, we introduce an adversarial model, which extends the multi-head model with a third decoder, whose goal is to infer the objective C from the latent representation set. The introduced adversarial training encourages the latent encoder to discard any spurious information encoded in the prompt, while trying to retain all causal features relevant to the final outcome. In this plot shown on the slide, the solid lines, so the lines over here, they represent the model's performance, the model accuracy, on the inconsistent examples, that is, the examples for which the objective differs from the type of the prompt. And so in the case of extreme confounding, we do not observe such examples in the training data at all, while when there is no confounding, there will be, in the training data, we would have an equal amount of consistent and inconsistent examples. In our results, we observed that the performance of all models significantly drops as the rate of confounding in the training data increases. The base model in blue is most heavily affected by this confounding. And then we have the multi-head model shown in green, which does a little bit better. But further, the introduction of the additional adversarial objective helps to mitigate the adverse effects of confounding even better. But ultimately, there is only as much as can be done on the modeling side. With a perfect confounding rate, there is no architecture that can disentangle the effects of the prompt types from the effect of the objective on the potential reports. So what can be done? To ensure robust generalization of reward models, especially in these multi-objective regimes, we suggest several directions for future work and research. Specifically in this paper, we vouch for more active forms of preference data collection rather than just relying on passively collected preference data. We also say that collection of rationals, not only preferences, may be helpful to identify the causally relevant latents. Then we also think about targeted interventions to ensure sufficient overlap in the latent space so that the assumption of positivity is not violated. And finally, we think about controllable LLM generation to enable these targeted interventions such that a response with a certain latent variable can be generated to test how this latent variable impacts the preference of a given individual. Thank you. And if you want to learn more about this work, please check out the full paper, which is now available on Archive.
Sure, for the super interesting presentation. And so the next part of today's session, I am pleased to introduce sort of the panelists for this session, and we are joined today by Dr. Simon Woodhead, who was the head of research and co-founder of EEDI, which Kasia just mentioned, and also by Dr. Rafik Salama, who is the head of R&D for data and AI at Accenture. Cool. So I'm going to stop sharing for a second. So I might start with you, Simon, since I know you work with Kasia and Antonin before. So from your perspective, sort of like, what are, from an AI for education point of view, what are the interesting applications here? What are the challenges? And what do you think are further issues that need to be addressed for it to be practically useful?
Yeah, okay. Oh yeah, lots to cover there. So education, a bit like healthcare seemed to be the other one that came up today, is a very sensitive area. So within the education setting, mostly the problems with any kind of generative tools use is hallucinations. So that remains a problem. And it really depends on the company as to whether or not they're happy to experiment with that or not. So we kind of have, on a scale, you have Carnegie went quite early with director students, and some of that's received some quite bad press. So we've been quite careful about what we've done there. And we've used a lot of human in the loop or teacher in the loop use of generative models or recommendations from generative models. In relation to Cassia's work, specifically the preference learning that we were just talking about, we see that as being a really nice way to encourage models to follow particular pedagogies, because teachers disagree fundamentally on the way that topics should be taught, or and they will necessarily want, if they are going to use tools, for those tools to follow the same pedagogies that they follow themselves. So we would be looking at kind of a preference learning, but not learning the preferences of the students who are going to receive the messages necessarily, but the preferences of the teachers or tutors that are working with those students. So that's sorry, that was one of the challenges. Do you want me to talk about the other work as well? The others are doing?
Super interesting.
Okay, so yeah, I was really impressed by the other work that I hadn't heard about prior to reading the papers that were shared earlier on this week. And I mean, I'm always, Cassia will tell you, and Antonella will tell you that I'm always trying to map things to the education space, even if they won't map very nicely. So I will attempt to map those two things to the education space. So the strategic planning or top-down approach to generation, absolutely love the idea of that being used within the education setting, because of course we cannot afford, or it's completely unacceptable really, to do a bottom-up approach in education in most contexts, and therefore if we're thinking of things like curriculum planning, I'm wondering whether this would be something which could help there. So again, we can go back to those groups of teachers who completely disagree. Could you have a number of prior beliefs from a group of teachers that are used to do the initial guiding, and then use this tool to explore and find the best curriculum within that? I don't know, but I'm looking for an answer from the team on that. I would love to know if that's possible. And then GSIM, in terms of simulation, the ability to create a student simulator, and I've spoken to Antonin about these kind of digital twins in the past as well. But if we were able to create a student simulator that could accurately or relatively accurately respond to things like the curriculums that we provide, the interventions which teachers do, that would be quite a game changer in education. And both of these things don't actually involve necessarily putting generative messages direct to students, and therefore I'm particularly excited about them because I think we can experiment safely with them.
Yeah, no, super interesting. I think some of the themes you touched upon, like sort of the active preference elicitation, sort of in Cassia's case, or the behavioral twinning of individuals, or like sort of having the same sort of quirks and behaviors, the bounded sort of rational behavior that we see in humans. I think those are all topics that we're all thinking about quite a lot in the lab as well. So definitely think there will be some things for us to discuss in the future. So now I want to sort of throw a question at Rafik, which is kind of similar. But I guess, like, from your perspective, with your sort of broad experience with consulting and working on different sort of industries, sort of what are your thoughts on how these works could be applied, and sort of what are the challenges that need to be addressed?
I think if I talk in particular about the papers, I think there's a number of things. I mean, that's I think it's a very interesting the work that was done around the strategy and trying to come up with a strategy for the reinforcement learning. I mean, we constantly try to identify a set of policies that work quite a lot for the reinforcement learning and try to adapt to those over time. So I think that is something that has been representing an issue for quite a lot of the applications of the reinforcement learning, and in particular trying to understand how do we adapt to them, or create a framework that creates a bit more of a meta layer that defines the policies. Obviously, I think like we was presented in the paper, the ability to react or predict again a bit more what's going to happen, and this whole closed loop is something that will be quite interesting. We've applied some of those in the past to quite a lot of problems, but in particular, for instance, this was applied in setting prices for the gas and the gas stations that that suffers from phenomena of very hike in price and then drop down quite slower. I think trying to set strategies, and even we've written that about 7 or 8 years ago, is the fact that we need to come up with some strategies. And if we're able to identify strategies, and that was a combination of human in addition to the AI, trying to come up with strategies and then trying to do that. But now we can start to see, obviously, that it's a natural evolution if agents can start to come up with some of those strategies, and then their ability to sense the environment and use obviously their own internal reinforcement learning to find the best strategies in the future as well might be useful. So I think that was quite an interesting piece of work, and I really like also the framework that was presented around GSIM and our ability to leverage or simulate a lot of the problems. Obviously, specifically in the clinical trials, there is quite a lot of work that was done in this area, and you can see some of the papers was presented even last year in Europe around the ability to do a hybrid digital twins of that, and Mihaela and I were kind of touching on that earlier as well today, on the ability to do dynamical systems with digital twin, hybridize that. I think that was quite super cool, and the idea to be able to create that the LLM would start to create that causal links and gradient tree optimization over time is something that is quite nice, and it does definitely have quite a lot of applications, and it also starts to touch on some of the issues that I'm thinking a lot about, which is how can I structure the layers of AI in pharmaceuticals, and how can we link some of those things, and you can see straight away that you can create some of those on top of the large language models. I think the various works that have been presented today have definitely have, and I don't think I'm going to have time to talk about all of them, but there is definitely even the preference learning and the ability to create those and explore all of those causal networks that we were talking about, and solve some of the confounding problems that we've got has got quite a huge amount of applications in the research aspects as well, and it's a lot of the research that we're trying to do by deciphering the causal links of gene expressions and the cause and effect that's coming out is quite an important piece of work, and I think it is quite a testament to how the whole field is evolving to drive for us some of those or to start to solve for us some of those problems that we have got in the real industry, and obviously in academia as well.
Yeah, that's super interesting. I mean, just sort of following up on sort of what you said, and you talked about sort of working with these digital simulators and coming up with these LLM agents that can generate strategies at scale autonomously, which is all super promising. But in terms of like sort of having these LLM based, whether it's a simulator or a strategy generator, these type of approaches, having them work in the real world, like what do you think are some of the obstacles that you've seen that like might have eluded the academia's attention in some sense. Don't know if you have anything interesting around that area.
Yeah, I mean, if your question is about does this start to make a shift in how we think about stuff in academic, I think definitely a lot of the it seems like a lot of the problems that we are trying to solve, like I was saying earlier, is a natural evolution to the and it starts to progress a bit more in the right direction of the various problems that we're trying to solve, and specifically how do we go back to older problems and resolve them with agents, or how do we go back to older problems that we've got and resolve them with large language models? That seems to be some of the things that we're continuously trying to explore as an academia. And I think the potential for us is that we try to identify where it doesn't work is as well as when it starts to work. So I think that is very important, because there's quite a lot of hype around the abilities of large language models and agentic AI to solve almost everything. So I think our ability to drive the solution, but also to drive when the boundaries of those techniques to solve and not other issues.
Yeah, that's super interesting. I think, Simon, I might ask you a similar question, but sort of, obviously in the education space, there's a bit more of a humanist touch to it, and this, student teachers classroom, and a lot of these sort of LLM agents and LLM-based ideas, and some of the works we presented today are sort of emblematic of some of the characteristics, I think. So do you see anything like in your space that sort of have maybe not really been talked about a lot in academia and research, but you think it's like a critical problem in education?
I'm trying to think if there's anything that's kind of been particularly missed. I don't think there's anything that jumps out as being missed. I probably would lean into this idea that we do need to be clear about where models shouldn't be used. So something which is commonly done at the moment there's a complete proliferation of new tools out there which are just wrappers of LLMs. So in education, there's I will not name any companies, but there are many companies which have done really well, like by just completely wrapping a vanilla LLM and serving that up. And there's also cases where companies are using LLMs to give really blunt things, like they'll ask an LLM, is the student proficient in this? And no rubrics, nothing, just based on a few questions. So which possibly undermines what people are doing with models, which are there's still other AI going on out there with other models which are trying to really capture patterns of learning and predict accurately and make claims about how accurate those predictions are. People are using LLMs for everything in that space without, and I don't mean the academics, I mean practitioners, developers are just seeing these tools and thinking that well, if they can produce text, they can produce numbers, they can, and all of these things are valid. So I don't know how aware academia is that is happening, but it is happening a lot. So I think from a practical point of view, I think that's probably the biggest problem. And the problem hopefully for problems like for companies like ours, where we are fully committed to research, we've been committed to research for a long time. We fund PhD students, we collaborate with researchers. It is then hard to make clear that you are doing things differently. So I think that for us is, I don't think it's a research problem you can solve particularly. It's almost a marketing problem. But yeah, that is a significant challenge in EdTech at the moment.
Yeah, no, that makes sense. I guess LLMs and LLM agents are not the magic bullet, and it's probably some mixture of traditional machine learning and more rigorous research that will create something that actually works in the world. Yeah, so thanks so much.